Suppose the greatest common divisor of a and some modulus is 1, and we want to solve ax congruent to b mod n. If we can find the multiplicative inverse of a mod n, we can multiply by it to get x congruent to a inverse b mod n. We could find the inverse using the extended Euclidean algorithm, but remember, a good way to understand mathematics is to solve the same problem in a different way. So let's see if we can find another solution. So again, it's useful to start with primes. Suppose we want to find the inverse of a mod p, where p is a prime number. Then we want to solve ax congruent to 1 mod p. And this corresponds to the difference ax minus 1 being a multiple of p, which we can rewrite as, since p is prime, the greatest common divisor of a and p is 1, so this equation has integer solutions that can also solve ax congruent to 1 mod p and minus py congruent to 1 mod a. Now the first congruence is what we're actually trying to solve, so it doesn't actually get us anywhere. But since presumably we've reduced a so that it is between 1 and p, the second congruence might be simpler because we can knock down this coefficient. So for example, let's try to find the inverse of 23 mod 37. So we want to solve 23 congruent to 1 mod 37. So if 23 is congruent to 1 mod 37, then the difference is a multiple of 37. And so we want to find integer solutions to 23x minus 37y equals 1. But these solutions correspond to solutions of the congruences. And again, this first congruence is what we started with, but the second one can actually be reduced. While we could solve 9y congruent to 1 mod 23, we note that it would mean finding integer solutions to a new equation. And we can solve that by solving a system of congruences. And again, this first congruence is what we started with, but the second congruence is new. While we could solve this second congruence, mod 9, we note that it would mean finding integer solutions to which we can solve by solving a system of congruences. And again, this second congruence can be reduced. So stop me if you've heard this. While we could solve this congruence, we note that it would mean finding integer solutions to a particular equation, which we can solve by, and again, we can solve the congruence, but we could also find integer solutions to, and finally we get down to a congruence that we can solve easily, u equals 1. So remember, we were trying to find integer solutions to 2t minus 3u equals 1, and we found u equals 1, so we find t equals we were trying to find integer solutions to 3w minus 4t equals 1, and we found t equals 2, and so that means w equals we were trying to find integer solutions to 4z minus 9w equals 1, and we found w, so that tells us z equals we were trying to find integer solutions to 9y minus 23z equals 1, and we found z, so we can find y. We were trying to find integer solutions to 23x minus 27y equals 1, and we found y, and so x equals, which tells us that the multiplicative inverse of 23 is 29. Now, while we might need to find the inverse in general, As long as the greatest common divisor of a and b is 1, we can solve ax congruent to d mod b directly using this method. So let's try to solve 7x congruent to 3 mod 23. Since the greatest common divisor of 7 and 23 is 1, there is a solution. Solving the congruence corresponds to finding integer solutions to, which corresponds to the congruences. The first one is what we're trying to solve, but we do get a second, simpler congruence. The second congruence corresponds to finding integer solutions to 5y minus 7z equals 3. We can find integer solutions to this equation by solving a system of congruences, where the second congruence is simpler and corresponds to finding integer solutions to. We can find integer solutions to this equation by solving a system of congruences, where the second congruence is simpler, and in fact a solution is w equals 0. If w is 0, then z is. If z is 1, then y is. If y is 2, then x is, which solves the congruence.